Alright, in this problem we're asked to look at a piston cylinder containing argon that undergoes an isothermal transformation. So let's begin by, after reading the problem statement, drawing a picture. We're told that we have a piston cylinder device, so drawing the cylinder and then the piston. In this case, we aren't told what the forces acting on the piston are, and so we kind of draw this little pin to say that the forces are unknown. What we do know about the transformation is that it's going to be isothermal. We have an initial pressure and volume given to us, pressure of 550 kPa, and a specific volume of 0.5/6 meters cubed per kilogram. We circle both of these quantities immediately because we know that the state postulate basically says buy two get one free. Given any two independent intensive thermodynamic properties, the others are determined. So in this case, we can find everything out about the thermodynamic state 1. From 1, we go to a second state, state 2. And the process that gets us there is that the temperature is constant. At 2, what we're told is that the volume has doubled. So in other words, my volume at state 2 is 2 times the volume at state 1, and in this case we've written this down in terms of specific volume. It's really the same thing as talking about volume, because if I multiply both sides by m, I would get V2 equals 2V1, which is the exact constraint that I'm told about in the problem statement. So let's before we finish, let's draw the blob, the most important thing here. So we're told that it's argon and gas, so we have substance and phase given to us in the problem. We're also told that the mass in this case is 0.6 kilograms. We're given a lot of information, more than we really need. We're asked to find the pressure at state 2, and also we would like to plot this in MATLAB. So let's look at how we solve this, starting off by writing down a governing equation. The fact is, we know that we're going to need an equation of state, at least at state 1, or at least we could use an equation of state at state 1, because the equation of state is precisely what connects P1 and V1. At 2, we don't know P2. What we do know, however, is that I can solve to get T1, which is the constant temperature of my transformation. In other words, T2 is equal to T1, and that would mean that I do know, in fact, two independent intensive thermodynamic properties at 2, from which I can get P2. So that's kind of the strategy for solving this problem, and it all lies with the equation of state. So writing down that we need an EOS. For that, we need to know the substance and the phase. In this case, the substance is argon, and the phase is gas. Because it's gas, I can use the ideal gas law. I could use any equation of state that's valid for gases. Van der Waals equation, a viral equation of state, or even a table if we had something like a table to use. At this point, though, let's go with the simplest case, and let's use the ideal gas law, PV equals RT, where R here is the gas constant for argon. So in order to use the ideal gas law, I need to know the substance, or I can't pick off what R should be. So now that I've got my equation of state, let's go ahead and look at these various states. At 1, ultimately I'd like to know what the temperature is, which is the temperature total for this period, for this isothermal process, and it's going to be equal to PV on R evaluated at 1, where I know all of those quantities. We'll wait and do these mathematical evaluations for numerical results in MATLAB in a second, but let's go on and look at state 2. At state 2, what do I know? I'm looking for P2, and P2 is basically just RT on V2. what we know in this case is that T1 and T2 are the same number. They're simply T. So we could write this down as RT2 on V2, where in fact this is just T1 and V2 is just 2 times V1. So what I can say then is my pressure at 2 is going to be equal to 1/2 times RT1 on V1. Well, RT1 on V1, that is going to be P1. So all that I've done here is divide the pressure in half by doubling the volume, which makes a lot of sense. Keeping the temperature. Begin plotting this in MATLAB. We'll do that. I'll use Octave, free MATLAB, and let's go ahead and start a new file. We'll call it argon, and we start with the secret sauce, clear, close all CLC, and then let's go ahead and put in the only constant that we have in this problem, which is the gas constant for argon. A quick look in Sengel's book gives us the argon constant to be 0.2081 kilojoules per kilogram per Kelvin. Kilojoules per kilogram per Kelvin. Kilojoules per kilogram per Kelvin. It's a good unit to remember. It's going to show up a lot. Then let's go ahead and put in our pressure at the given state 1. And then after we've input that pressure, and also we know that the second volume is going to be 2 times the initial volume, let's go ahead and solve for our intermediate value. So the isothermal temperature of this process is just P1 times V1 on R. And of course the units that come out of this are Kelvin. So we have kilojoules per kilogram per Kelvin in the denominator, and on top we have kilopascals times meters cubed per kilogram. It turns out that a kilopascal times a meter cubed is a kilojoule. So everything cancels here except for the Kelvin unit. And then we're going to also write down P2, and then rather than just writing it down as P1 divided by 2, let's just compute it, RT on V2, and see what it gives us. So this would come out in meters cubed per kilogram, and we run our code, and we find that the temperature here is 220.25 Kelvin, which I would write down on my sheet and box, and that the pressure is 275 kPa, which is indeed 550 kPa divided by 2, and I would box that. And the thing that we need to do is actually plot this process, and we probably want to plot this in the PV plane. So in order to plot this in the PV plane, we're going to need to know what our pressures are and corresponding volumes at each one of those pressures. So let's go ahead and we know that our volumes are going to run between V1 and V2. And let's go ahead and put 100 points in there. So now we have some volumes, and for each one of those volumes we want a pressure. Now the equation for pressure for an ideal gas would be P equals R times T on V. And in this case, the temperature is a constant. So R over T is a constant. V, on the other hand, is a variable, right? We're plotting in the PV space. And this is going to be a hyperbola, like 1 on x. And then we're going to plot these, the pressure versus the volume. Oops, excuse me, the volume on x-axis, the pressure on the y-axis. And go ahead and put some labels on this. So V in meters cubed per kilogram, and P in kPa, And let's go ahead and plot this. And so here we can see our initial state. We had a pressure of 550 kilopascals and a volume of about 0.08, 0.5 on 6. And we drop all the way down to a much smaller pressure, 220, and our volume is basically doubled. So this is our plot.